Okay, looks like we're recording. Okay, great. So here's where we were last time. We were talking about surface independence. And reminder, surface independence is a lot like path independence. It's basically the same idea. It's just that we're looking at two surfaces that have the same boundary curve instead of two curves that have the same boundary points, right? But otherwise, other than everything is one dimension lower, all the same ideas, right? So the idea with path independence, by having the same starting and ending points, the line integrals are both equal across both of those curves. And analogously, with surface independence, when two surfaces have the same boundary, the flux integrals are the same across both of those surfaces. Okay, all right, so this is about where we ended last time. I think I may have given some discussion of this down here, but let me do it again just to be thorough. So again, the idea, we have a first surface, and we have a second surface oriented in such a way that these two surfaces have the same, and I forgot to highlight that they have the same boundary, so the same boundary curve in this case. Keep in mind, of course, a boundary of a surface is a curve. Right, so here's our scenario. Reminder, the orientation is a little arguably, I'm going to say counterintuitive. I think that's maybe a little strong. It's not what you would think at very first glance, but it's easy to confirm that these are the orientations that you have to do in order to make the boundary orientation the same for both boundaries. Okay, so so let's apply Stokes's curl theorem to the flux through the first surface. This, by the way, notice, assuming that we are talking about a curl field. And applying Stokes's curl theorem, right, gives us the boundary line integral of the anti-curl. Okay, now we do the same exact thing on the second surface. Again, same integrand being the curl of a given vector field, and again, because they have the same boundary, we get the same resulting boundary line integral. So these two fluxes are the same because they're both computed by the exact same boundary line integral because they have the same boundary. Right? So that's why it works. Shocking fact, not only are there surface-independent vector fields, but there's a bunch of them. Anything that's a curl is surface-independent. So, neat fact. All right. So, by the way, this does go both ways. This other direction is harder to prove. It's pretty straightforward to prove that every curl is surface independent. Harder to show, but also true, every surface independent field is a curl. And a quick reminder, I am ignoring regularity issues. Again, not really what this course is about. So there are some worries when you start talking about this sort of thing of, is there a differentiability problem so much as at a single point even can throw a wrench in the works pretty badly. So here we're going to assume that we have all nice everything. Okay. So now that I think about it, maybe we did talk about this a little bit as well. Does anybody remember? Did I start on?
I think this is a little further back than we actually got to, maybe.
Oh, okay. So so we're doing some repetition. Could be worse. Okay. So now very similar setup. You'll notice this picture looks a lot like the previous. So again, we have a surface oriented like so, and another surface oriented like that, and again arranged so that these two surfaces have the same boundary curve. Okay, notice then further that I can think about then the solid on the inside, so what I'm going to call R, the solid on the inside, that's a three-dimensional thing. that solid on the inside. If we ask, well, what's the boundary of that solid? Well, the boundary is it's these two surfaces, S1 and S2, right? But don't forget, when you say the word boundary, right, you talk about the boundary of a solid. Boundary means oriented in a particular prescribed way. And again, arbitrary but standard. And boundary, as we're looking here, boundary of R, oriented away from the solid, which means in the same direction that S1 points, but opposite of the orientation that S2 points. And so that boundary is S1 minus S2. And this issue right here, the fact that the orientations are opposite on S2, is why we have that minus sign right there. Okay, so hope everybody remembers this from last time. This is kind of a weird setup, but I do want to point out, and I think this is worth observing, that this is actually very familiar. This setup here that we've arranged of a three-dimensional solid created by two surfaces with the same boundary curve, totally analogous to what we have over here, where we have a two-dimensional surface between two curves with the same boundary points, right? Totally analogous. Notice I've laid it out on the page the same way. This, again, no accident. I wanted the analogy to be very strong. Notice even that we have the minus sign in the same place, right? The analogy is very, very strong. It's a real eyebrow raiser. Again, that's on purpose. Okay, all right. So that sort of suggests that maybe something kind of like what we did over here might be useful here. We applied Stokes's curl theorem to the surface. The highest dimensional thing over there on the left is that surface. So we apply Stokes's curl theorem to it, write it down, and then good stuff follows. So I'm going to do the same thing over here. I'm going to apply the relevant boundary theorem, accumulation theorem, whatever you want to call it, to the highest dimensional thing in this picture. Button. Where's that button? Oh my God. The highest dimensional thing in this picture is our region R. If I can get my highlighter to work. So I'm going to use R. We're going to write down the divergence theorem. There it is. The divergence theorem says that triple integral of divergence over the solid is the flux over through the boundary. Just you got to keep in mind you need divergence to be the integrand over here. Is everybody comfortable with that? I'm just applying the theorem to this carefully constructed setup. Okay. And having done that, now I'm going to clean up my picture. I'm making a mess here. There we go. So now to this. Keeping in mind this minus sign here requires that I have a minus sign there. Right? Now we're going to make arguments that are totally analogous to what we did some pages back. So in particular, let's consider the scenario. What would happen if divergence were 0? Let's just think about it, right? If the divergence is 0, that means that this integrand is 0. That means that this integral is 0. So the left-hand side of the equation is 0. Being as it is an equation, that means the right-hand side of the equation is 0. That means that whenever we have any two surfaces, S1 and S2, per this picture, in other words, whenever we have any two surfaces with the same boundary curve, right, the difference between those two fluxes must be 0. In other words, those two integrals must be equal, which is what it means for a vector field to be surface independent. And as we saw on the previous page, that means it's a curl. Now, again, it doesn't show you the reasoning there. That's inaccessibly hard to do, but true fact. Okay, and then turning it all around, everything still works. Suppose you have a curl. Hypothetically, let's just say, well, if a vector field is a curl, we know it's surface independent. If it's surface independent, that means that these two integrals are equal. That means that difference is 0. That means the right-hand side of the equation is 0. That means that the left-hand side of the equation must be 0. Now, how is this possible? How could it be that a triple integral is not just 0, but it's 0 no matter what three-dimensional solid R domain you pick? All domains, all integrals are always 0. There is only one possibility, and that is that this integrand, the divergence, must be 0. There we go. Okay, so again, analogous reasoning. I mean, geometrically different, right? You got a different picture to look at. Where's my? Here it is. You got a different picture to look at here, but totally analogous. All differences acknowledged. Totally analogous to some similar reasoning we did with Stokes' theorem for surfaces defined by curves with the same boundary points. Questions? How is everybody okay? All right. By the way, quick recognition, I'm sitting here instead of in my usual spot with the podium because there's just a ton of ants over there, and I'd be basically standing in ants, so I appreciate your flexibility. I'm just going to sit over here today. Yeah, they go all the way over to just right halfway down the wall there. Yeah. Okay. All right, back to it. So neat fact. We talked about surface independence. We see that surface independence comes about if you have a curl. Oh gosh, so much to erase. But being a curl, we see some reasoning here that promotes that being a curl is simultaneous with divergence being 0. So that means that divergence being 0 can serve as a test of whether or not a vector field is surface independent. And let me show you how we can use that in a calculation. And again, this is not a bunch of abstract nonsense. This is a powerful computational tool. And here's how such questions might come at you. Notice in the statement of this question, it just says compute the flux, right? Vector field given, surface given in a weird way, but whatever. That's life. It does not say anywhere in here, hey, by the way, use the following trick to compute the answer to this question, right? This is not a question where the answer is half given to you. Just, hey, compute the flux. And now you've got to decide for yourself what I like to call diagnosis. How do you decide which method are you going to use here? And we'll talk more about how to do diagnosis later today, in fact. So what am I going to do here? I'm going to start off just going down the road that gets to the answer. Again, I will talk later about what makes me think to do what I'm about to do here. But let me just compute the divergence of this given vector field, my integrand here. I'm going to compute the divergence. Easily done. Divergence is 0. That immediately tells me that my vector field is surface independent. Everybody happy? Okay. All right. By the way, real quick computational trick. Notice not only is the divergence 0 here, it's what I'm going to call obviously 0, because it's not like a bunch of stuff cancels. It's like it's all zeros. We're adding up 3 zeros. Not that that's necessary, right? 0 can come about from cancellation, but you could just immediately see, look, there's no x's in here, there's no y's in here, and there's no z's in there. So when I take the appropriate partials, you don't even really need to write it down. You can say, look, no x's, no y's, no z's. Boom, divergence is sum of 3 zeros, so obviously 0. Nice little trick I like to point out. Okay, so surface independent. So now before I can pick a new surface, I do need to understand the original surface. So let's take a look at our original surface here. We've got a kind of an elliptical paraboloid there. flashbacks to chapter 2, right? And how to, no, wait a second, I'm sorry, that's the wrong book. Flashbacks to chapters 12 and 13, I guess it is. Probably mostly chapter 12. This is an elliptical paraboloid. If you're not clear on why that's an elliptical paraboloid, make sure to remind yourself how that works. But very importantly, we're looking for the part of that elliptical paraboloid where z is greater than or equal to 0. Okay, so let's think about what that looks like. Here's a picture. There's an elliptical paraboloid like this. Z equals 0 is like this. So the part that is above z equals 0 is this right here. Everybody good? Okay. Now, tricky bit. When drawing this picture, you're going to want to draw the lip kind of along the bottom there. And then having drawn that lip, and you look at the picture here, it kind of looks like you've got two parts of this surface. Just looking at what I've drawn, right? Not thinking about the phrasing of the question. Just looking at what I've drawn, there's the curvy part up there, but then it's tempting to, again, just looking from my picture, it's tempting to think that my surface, my originally given surface, has a bottom face, because I kind of looks like I drew that. Very importantly, though, that's the drawing misleading you. Art is hard, I grant that. I don't really know a good way around this problem other than to be careful with the interpretation and don't let your drawing mislead you. Let's look back at the statement of the question here. It does not say here, this surface, and part of the plane z equals 0. That's just not what it says. Right? It says very clearly that we're looking at a part of this paraboloid. That means that S is entirely a subset of this paraboloid. These points down here are not on that paraboloid. These points in what I'm eventually going to call S2 are just not in any way part of S1. Everybody clear on that? And again, this is a nasty little landmine. You can get in real big trouble. Misinterpreting the question like this, it's tragic. If you're not comfortable with this, say the word now. I'm very happy to pause and elaborate. Okay. Yeah, okay, so our surface S, just that part right there. And just to avoid confusion, I'm not going to draw the lip at the bottom. Okay, so surface independent. Great, cool. Surface independent means I don't have to use this surface. I can switch to any other surface I want. Okay, well, let's not overstate it. It means I can switch to any other surface that I want, which has the same boundary, right? So I was given originally some surface S1 to compute the flux through. I am now allowed to switch to computing the flux through any other surface S2, but again, very important requirement here. It's got to have the same boundary as S1. Real easy mistake to make, to forget this condition, a very, very important condition, of course. So we've got to find another surface that has the same boundary. So I guess I'd better spend a little bit of time thinking about what the boundary of this surface itself actually is before I throw it away. I have to understand what its boundary is, because that's my responsibility. So not hard to persuade yourself that the boundary is going to be this lip thing. But we do have to think through orientations. Notice it says right here that my original given surface oriented upward. That means that my given orientation is like that. Again, remember there's a sloppiness and kind of a casualness to the terminology about orientations. When it says upward, it doesn't mean directly, exactly straight up. It means of the two options. Hopefully, presumably, only one of them should be in any sense described by the used language. And again, of our two options, upward and downward, there's really only one way to interpret. Okay, is everybody comfortable with all that? All right, so there's my orientation. Now, what does that mean about the orientation on the boundary here? And again, you got to play the right hand game. Right hand, very important. Even though you have a pen in your right hand, don't just use your left hand for convenience. You'd be surprised. I did something analogous to that one time in a home carpentry issue. It's dumb. Anyway, so right hand, thumb in the direction of the surface orientation. You look at your fingers of your right hand, that defines a swirl, which is like that. And if you were to drag this picture here down closer to where the boundary is, notice that gives me a side swipe, and that gives my orientation on the boundary to be this way here. Everybody happy? Okay. All right. Cool. Let's see here. Let me go ahead and put this back up there. Okay. So, great. We have our original surface. We understand its boundary. Orientation included. And so, okay, now I get to invoke my surface independence, and I'm going to say, you know what, this given surface, phooey on it. I don't need it anymore. It served its purpose. I understand its boundary. I am now going to say I get to pick any surface that I want that has this same boundary. Now, of course, you have a bazillion options. You could pick a great big ellipsoid up there, or you could, my favorite silly example is you could make a glove-shaped surface like that, right? I suppose, free country, I don't see that that's a good idea. There's usually a pretty obvious choice. Now, again, I can manufacture counterexamples, but usually the obvious choice is going to be the best choice. So in this case, look, my curve is sitting in the XY plane. Don't you think it makes sense we should just choose the relevant portion here of the XY plane? Yeah?
Can we just go over again why S2 isn't in S? Or the entire idea of like how...
Oh, yeah. So it's all about the way this is written down. So let's look at the way this is written. It says S is part of the ellipsoid. It doesn't say part of the ellipsoid and also, right? So all this business about, with z greater than or equal to 0, that's modifying and telling you which part of the ellipsoid I keep saying ellipsoid, I'm sorry, elliptical paraboloid. It's telling you which part of your paraboloid is S. Does that make sense? Yeah. But there is this urge, and again, I blame the art in the act of thinking about what happens when you cut it by the XY plane and thinking about that boundary. You end up drawing a picture that looks like it has a bottom to it, but it's not part of what the surface was.
It's still just that curve.
It's an upside down bowl,
Got it, yeah.
right?
Yeah.
The cereal does fall out. This is not like a Tupperware situation where it's also got a saran wrap, kind of a deal, right? Yeah, no, the cereal falls out. Is everybody happy? Everybody's good. Okay, so new surface. Here is another surface, S2. Just the relevant part of the XY plane. This surface has the same boundary, doesn't it? Isn't that nice? But it's a much nicer surface. Now, again, we got to think about orientations. Again, orientations are not free. This is, the business about orientations is arguably one of the more sophisticated and challenging aspects of doing this, using this tool correctly. So again, keep in mind, scoring on an exam correspondingly in recognition of how significant and sophisticated and challenging this idea of orientation is. So even though it only amounts to a minus sign, that's not the point. It's not about the answer, it's about the reasoning. The reasoning is significant, right? So expect for orientation mistakes to cost you, but let's be much more optimistic about that. Expect to get lots of good points just for correctly interpreting the orientation. Right? That's the glass half full interpretation there. Okay. All right. So let's think about our options now. Again, let's start with the wrong answer just to show how we know it's the wrong answer. I could imagine an orientation on S2 that was downward. I'm going to put a question mark here to recognize that we don't know if this is. We're just asking this question, and then you think, okay, well, right hand, thumb, down, swirl. The swirl then goes around. That was the worst. Goes that way, which is just the wrong way. Everybody see that? All right. Well, so tried, but that's not it. So now we ask, what about if it went the other way? What if we had our normal vector pointed upward? Then thumb, right hand, fingers, swirl, goes around like that, which is the correct way. So this is the correct orientation. Does that make sense? Now, let me say a couple more words about whether that's reasonable or not. Let's see here. I'm going to do that. Okay. Is this reasonable or not? It's tempting to look at these two orientations, the orientation on my original surface and the orientation on my new surface, and say, well, they're kind of opposites. Right? One's inward, one's outward. Aren't those opposites of each other? They're not. They're neither alike nor unalike. They're on different surfaces. You really cannot make any meaningful, you cannot make any absolute comparison between orientations on two different surfaces. They're totally different surfaces. There's nothing we can, it just doesn't make any sense. So try not to think about these as whether they are the same or whether they are different. Right? Now you can and must ask whether they induce the same orientation on the shared boundary. Yeah. But there's a lot more meaning there. We're indicating that we're looking at the shared boundary. That defines a sense in which we can, in some sense, compare these two orientations. You can also ask a question about, are they the same or different in terms of thought of as part of the boundary of this whole, right? And as part of the boundary of the whole, they are kind of opposite in the sense that one is consistent with this boundary and one is not consistent with this boundary. Right? But there's two perfectly reasonable senses in which you could try to compare these orientations. Neither one of them is absolute. Neither one of them is the right way to do it. And so I think the best advice is just don't try to compare these orientations at all. They're on different surfaces. The question is not whether they're the same or different. The question is whether they are right for the job that they're doing. Everybody happy with that? It's an important point. Okay. All right. Well, we're in business now. We've got ourselves a new surface here. Oriented and everything. I'm going to use this new surface instead of my original surface. Surface independence and all that. Gotta love it. And now I have a different question to look at, and everything's going to work out quite a bit more nicely. Let's see. Oh, and I'm going to zoom out so I can see the details here. Let's look at our vector field G. And we're going to dot that now with our, let's see here, we have our new normal vector N2, which, by the way, I can just see what N2 is. N2 is perpendicular to my new surface. My new surface conveniently chosen to be just flat. Its normal vector is obvious. It really is 0, 0, 1. Right? Yeah, question?
If you have it like 0, 0, -1.
Mm-hmm. Yeah, if the orientations were set up different in the question, then yeah. No, but here it has to be 0, 0, +1 because of needing to have the same orientation on the shared boundary. Yeah. Is that cool? Yeah. Okay. So this is a pretty easy dot product at this point, right? This dot product, I just need to dot G with 0, 0, 1. So that dot product is just XY. And this is an easy integral, and it's 0 by symmetry. Gotta love it. Again, let me remind you, we have symmetry rules we talked about earlier in the course, and scalar surface integrals, which this is. Right now that I've done the dot product, I've dotted out the orientation aspect of what had been a flux integral. Now is literally just a scalar surface integral, and odd symmetry arguments work just fine. And this is 0 by symmetry through the x-axis. Everybody happy? Yeah.
Could you explain why S2, any surface above it, has the same shared boundary?
Explain why what now?
The boundary of S2 share the same boundary as S.
Oh, the original surface. Oh, yeah. So the original, this is mostly just a geometric appeal, but the original surface looks like this, right? And my new surface, I'm defining as follows. Let's start with my original surface. My original surface's boundary is an ellipse. And I know that because this is what you get when you take the xy plane, and which is z equals 0, and you plug in z equals 0 into that equation defining my original surface, and you literally get an ellipse, right? So this turns into just an ellipse. Is that cool? Yeah. Now, once I have that that's an ellipse, then defining S2 is just a matter of saying, okay, well, let S2 be the part of the xy plane that's inside of that ellipse.
And because it's we found it's a curl field, we can do this for any. We can say it's surface independent for any curl.
Yeah, I didn't even have to invoke the fact that it's a curl field. I just observed that the divergence was 0, and that alone is sufficient to say surface independent.
And this applies for we can just find the projection onto the xy axis for any curl field.
I don't follow. I'm sorry.
Since here we just found the projection onto the xy.
Nope, it's not about projections. It's about finding a surface with the same boundary. Now, coincidentally, I guess you might say, this surface and this surface, yeah, sure, the blue happens to be a projection of the green. That won't always be the case. So that I would call that coincidentally, yes, right? But the meaningful point, the thing that actually makes this work, is the fact that these two surfaces have the same boundary. Is that cool?
Yeah.
Yeah. Everybody happy with that? Yeah. Okay. Cool. So one other thing I wanted to say. So you'll notice here, I did not supply the details for the symmetry argument. So I'm going to say two things about that. One is, make sure you can do that. It's important to be able to think through and understand symmetry arguments are delicate. They're little landmines, potential landmines. You don't want to accidentally forget to check. I forgot to check if the integrand has odd symmetry. The domain I thought about, but I forgot the integrand, or whatever. Right? So make sure that you're comfortable with how to make that argument. Second thing I want to say about this. Symmetry arguments I view as being primarily a thing about Exam 2 material. And so for Exam 3, you do not have to supply all 5 checkpoints on a symmetry argument. You're welcome to do what I've done here, which is just 2 things. First of all, you have to declare that something is equals 0 by symmetry, right? And you have to be right about that. Right? You can't just start declaring stuff to be 0. And secondly, you do have to tell me what is your line or plane of symmetry. So you got to give me something. Right? So line or plane of symmetry, that'll be sufficient for Exam 3. Is that cool? Everybody clear on that? Okay, so you don't have to prove that the integrand is odd, and you don't have to blah, blah, blah. You have to be right, and you have to give me the plane. Line or plane, whatever. Okay. All right. So now we get to a bunch of stuff that we've actually already done. Again, we did these in the Chapter 219 notes. So moving through these Math 212 notes, we've already talked about magnetic fields and current flow fields, etc. This business here about physical construction of an anticurl is fun stuff when I have the time, which is increasingly rare these days. But anyway, we're not going to talk about this. It's a cute idea if you want to take a look. If you're going to be doing something physicsy, this is, I think, worth thinking about. It's a fun fact. But we're not going to cover that in this course. You're not responsible for it. This business about Maxwell's equations, we've actually already talked through this stuff, at least concerning magnetic fields. And so again, I'm not going to repeat that. There's an analogous argument about electric fields, and again, that's more of a physics thing. So we're not going to talk about that. And this example here is a physicsy example that I don't think we're going to have time for. Again, this is pretty optional stuff, so I'm just going to skip that as well. So we're kind of done with Chapter 15 at this point. That said, there is a lot going on. I think it's worth reviewing. So I am going to review a bunch of the ideas, talk about the big picture, talk about how to interpret certain facts that we've discussed on the diagrams. I think the diagrams are really, really important, as you all know. So along those lines, here we go. Let's talk about our theorems. Here are the various different, what you might call accumulation theorems, because all of these theorems are talking about accumulating quantities. Right? The first step of all of these theorems is to identify what is the relevant accumulating quantity. So I call these accumulation theorems. I also sometimes call them boundary theorems, because all of these are about accumulating quantities being computed only on the boundary. Right? So that's kind of cool. So accumulation theorem, boundary theorem. I also sometimes call these density theorems, because the integrand of the resulting integral is always something that can be interpreted as a density. So pick your favorite. The fact that there are so many common features of these theorems, right, that I can't even decide which common feature to name them after, right, I think is pretty cool. Okay, so in all of these theorems, there is an accumulating quantity in question. Make sure you have this straight, right? You want to don't inadvertently think that with Gauss's theorem we're computing circulation or something. Nope, not at all. Right? Gauss's theorem is about boundary flux. Okay, so in all of these theorems, there's an accumulating quantity. All of these accumulating quantities are computed with integrals. Integrals over the resulting interiors. And specifically, integrals of, now you'll notice here that they're all densities. It's always an integral of, the associated density, the notion of density associated to the accumulating quantity in question. So if you're computing change, then you get change density, blah, blah. If you're computing circulation, you get circulation density. A couple of them are oriented. True, right? But aside from that, change density, flux density, circulation density. Everybody good so far? Okay. All right. So really, the main distinctions between these theorems is what these resulting densities are. Change density in the single variable context is just a derivative. And again, I really like this idea that in some sense, this is kind of the seed from which all the rest of this grows, right? This idea that we're talking about change as an accumulating quantity. We're going to view density as quantity, this stuff like quantity per unit size, and just a matter of kind of interpreting what that ends up being. And sure enough, it ends up being the derivative. We got lucky on that one. Right? But likewise, analogously, all of these other integrands that we've seen in all of these various other theorems. They're just the associated density. Density of the accumulating quantity in question. Okay, so the purpose of this page is just kind of to serve to remind you, for one thing, about some of these ideas, but also to underscore the very strong pattern that holds all these theorems together. Is that cool? Yeah. Mm-hmm.
Could you explain why the fundamental theorem of line integral is so limited?
Why? Sure. So if you look at the way the fundamental theorem of line integrals is written, I'll write it down up here. So we're talking about FTLI and f of b minus f of a is an integral over the curve in question of a gradient of f dot t ds, or otherwise thought of as integral gradient f dot dx. Right? So the idea is you can think of this as stuff per unit size, in which case this is literally a density. That's a scalar density because it's stuff per unit size. Right? But instead of thinking of the piece of curve in question as having a scalar size, if you just look at how it's written on this side and notice that this is what you might interpret as an oriented size, and that's a stretch, right? That's I'm broadening the idea of what size is to include the fact that, hey, I also want to talk about which direction it's pointing, right? So stuff per unit oriented size, I then interpret this as being an oriented density. Does that make sense?
Yeah.
So there's, so go ahead.
Sorry. What does it mean for the sign? If I interpret it as like work, so does it mean like if it's going in one direction, it's negative, it's going
Yeah, that's one way to think about it. Yeah, but it's more than that. It's not just a question of negative or positive. It's that, think of it like this. So the gradient points uphill, right? So the gradient is telling you whether the mountain that you're climbing up is, how steep is the mountain. But it's also telling you in which direction that is uphill, right? And so if you're hiking along a trail on that mountain, it's probably not going straight up. Let's hope, right? They do switchbacks, right? They do the zigzag, and so the trail is actually going this way. So the gradient is telling you two things. It's telling you how steep the mountain is, but it's also, by virtue of the fact that it's got a direction, it's telling you, hey, what do you dot with your direction to see how steep you're actually going to experience as you climb along the trail. Does that make sense?
That makes sense, yeah.
Yeah. Cool. All right. Okay. Moving along. So here's our diagram. This is the two-dimensional diagram here. And let me, I want to go through and kind of mark up this diagram. The first obvious thing, and I've done this a million times. Oh, it looks like we're running out of battery. Why don't I go ahead? This is a good point to go ahead and make a switch. I'll plug this thing back in. I'll use my finger. Okay. Old news, old fact. Operator to the right, boundary to the left, evaluate on both sides, you get the same thing, right? Likewise, for the other sort of spot in this diagram, operator to the right, boundary to the left, evaluate on both sides, you get the same thing. Right, so these theorems, totally different theorems. Green's theorem and fundamental theorem of line integrals, totally different theorems about a totally different context. A two-dimensional region with a boundary curve, totally different from a curve with boundary points, right? And yet extremely analogous. And the diagram really illustrates the analogy, right? The diagram is the how to say, this diagram argues, I think, for how strong the analogy is. Okay. All right. Here's another thing I want to talk about on the diagram. And this is what I've got written down below here. There are some special vector fields. And I just want to remind you how to think about the special vector fields. Specifically, we're talking about gradients. Right? Gradients are special vector fields. And they're special in various senses. Let's see here. For one thing, these special vector fields, there is a function whose gradient gives you that field. Yeah, absolutely. That's one of the features of these special fields. Now, here's another feature of these special fields. Green's operator is 0. Now, I emphasize that this is one property of these special fields. This is a different property of these special fields, but it's the same fields, same vector fields, just different features of these fields. Okay, and then there's a third one, and the third one is path independence. Let's see here, well, real quick, let me, just for color coding purposes, being a gradient, right? We talked about on the diagram, Green's operator being 0, in other words, the vector field being irrotational, right? Recall that word, irrotational. And now the third property, path independence. And I want to talk about how path independence shows up on this diagram. So path independence shows up as follows. If you have two curves whose boundary points are the same, that's just, I don't know, I'm not being rigorous, precise about this, but to me that's what I see in my mind when I see two curves with the same boundary points. That to me that's just a convenient way to represent that on the diagram. And the big idea of a path independent vector field is, again, whenever you have two curves with the same boundary points, you get the same value for those resulting line integrals. Okay, so that's what the three most important properties of these special vector fields look like in this context, in R2. Everybody okay with that? All right. Now, let's talk about in R3. And again, we have special vector fields. Our special vector fields here are vector fields which, on the one hand, we've got gradient fields. We also know that gradients are the ones where the curl is equal to 0. And reminder, again, curl as a way of measuring how much of a rotational aspect of the fluid there is. Curl being 0 means there is no rotational aspect, and thus the term irrotational. So just a reminder, right? And again, the other shared property of these vector fields is that they're path independent. So let's draw this on our diagram. And this is going to look very familiar because we're talking about, again, the same vector fields and kind of the same properties. They're the gradient of something, aka they have an anti-gradient. The curl, not Green's operator, we're not in 2 dimensions anymore. The curl is equal to 0. And path independence, whenever you have two curves with the same boundary points, you get the same line integral. So notice here the little pattern that we have there for the special fields in column 1 of R3. Same exact pattern as in R2. How about that? So different theorem on the right? I mean, Green's theorem is not the same theorem, but it's totally analogous to Stokes' curl theorem, at least in this sense. Okay. All right. Let's see here. Now, going on, and let's talk about a different collection of special vector fields. Different collection of special vector fields. Not gradients, but curls. for which divergence is 0. AKA they're surface independent. Now, these are all really different. Being a curl and being a gradient, very much not the same thing. Right? Divergence being 0, very much not the same thing as curl being 0. Curl and Green's operator, a lot of people consider them kind of the same thing because they measure the rotational aspect. One's 2-dimensional and one's 3-dimensional, but they serve the same role, highly analogous. Not divergence. Divergence is about fluid source and fluid sinks and stuff like that, right? Totally different physical concept. So, but let's take these special vector fields now, right? We've already talked about these properties being simultaneous. Any vector field that's one of these is the other two. Also, regularity issues ignored. What does this look like? Well, these vector fields being a curl of something, divergence being 0, and being surface independent. Now, how am I going to draw surface independent on this diagram? Well, this vector field has the feature that whenever you have two surfaces with the same boundary curve, you get the same flux. And what I think is awesome is that this little diagrammatic representation of these ideas, totally different vector fields, right? But this representation of these vector fields, notice again, identical to this representation of those vector fields. So they're not the same vector fields, but these properties are highly analogous to each other. It's literally like I can take this little drawing here representing these features of our path-independent vector fields, and I can just slide it over like that, kind of. I didn't line it up perfectly, sorry. So, path independence, surface independence. Is everybody with me? So, I think this is really powerful stuff. Again, if you understand the pattern, we've just cut in half how much you need to understand, right? Because the pattern, at least on the diagram, as it applies here to path-independent vector fields, same pattern applies to surface-independent vector fields. Is everybody good? In fact, I can strengthen this pattern a little bit, and this is a fun little exercise. So let's see here. How was it? I gotta get some color choices made. I better use there we go. Okay. So path independence. How was it that I argued that every gradient was path independent? I used the fundamental theorem of line integrals. Oh, I didn't want to be in that mode. Sorry, I wanted to be in the highlighter mode. There we go. I showed that gradients are path independent by way of the fundamental theorem of line integrals. Right? How did I show that every curl was path independent? How did I make this connection? Well, it was with Stokes' curl theorem. Okay, well, check this out. That pattern continues as well. So the argument that I made, if you think back to at the appropriate time, the argument that I made to argue that every curl is path independent, we used Stokes' curl theorem. And how did we show that every path independent vector field has divergence 0? We used Gauss's. Oh, come on, colors. I hit the little thing there. There we go. We use Gauss's divergence there. So not only the results, but the arguments that we made, totally analogous. Powerful stuff. Is everybody cool? You can use this analogy for yourself. If you forget a lot of this stuff at some point, let's see here, by the way, let me clean up a little bit. here. First, if you kind of forget how some of this works, and if you find yourself needing to remember, oh gosh, let's see here, wait a minute, how do I show, with this, hard to use the colors here, how do I show a connection between curl and surface independence? Again, how did that work? I don't remember how to come up with curl and surface independence. Well, when we were talking about path independence, perhaps you'll have an easier time remembering that the fundamental theorem of line integrals made that argument for you. Once you remember that, then you can say, okay, well now back to this context, how would I make a connection? Again, we ask, how would I make a connection between curl and surface independence? And the pattern suggests, hey, use Stokes' curl theorem. And the diagram has now helped us with our homework, right? The diagram has suggested an idea to try, and it's the right suggestion. Everybody on board? Okay. All right, so I'm a big fan of these diagrams. I hope you'll jump on board and use these as we're describing. And now I better fix. Let's see here. Yeah, okay, I've got this in the wrong spot. Let me move this back. Like so. Okay, cool. Okay. Okay, is everybody good? Okay. What I've got now is a bunch of examples. And in particular, I'm going to switch over to the Math219 notes. This is Math219, Chapter 7. Let's see here. This is page 33. It seems. It's just, again, a little bit easier to read, a little bit more cleanly written, but these are the exact same examples that I have in the Math 212 notes. Again, it's just a little easier to work with here. Diagnosis. How do you figure out, right, you've got yourself in a situation where you need to compute either a line integral or a surface integral. What do I do? Right? What's the process? So I am a big believer in the diagram, right? So I do think the first thing you should do is identify where is the question on the diagram, and then let that context give you some candidates. So let me show you an example of what I mean by that. Let's suppose you've been asked to compute a flux. Let's just say. And the question says compute the flux of the blah, 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 blah. Okay, well, there's flux. Everybody see what I mean? Therefore, here are two theorems that use flux. So it suggests a couple of possibilities. It's possible, I suppose, I might compute the given flux by reinterpreting it as a line integral by way of Stokes' theorem. Also possible, I might compute the given flux by interpreting it as a triple integral using the divergence theorem. Couple of reasonable candidates of things to try. Everybody with me? Okay. Now, I will observe also that the diagram suggests some things not to try, not to waste your time with, and frankly, some things that you shouldn't even put on the page because it looks bad, right? But there's no way the fundamental theorem of line integrals is going to be relevant if you're computing a flux. It's just not. It's way over there. Right? It does not hook up with the object in question. So whether or not there is an anti-gradient doesn't matter. Anti-gradients have nothing to do with the question. The question was to compute a flux. Right? So all of basically anything to the left of this line here, just keep that off of your work. It couldn't possibly be relevant, and it just makes it look like you're not making the right connections. Does everybody see that? So this is kind of a strategic advice, I'll call it. Don't make your work look bad. Okay. So likewise, let's clean up my picture. If you are asked to compute a line integral, here you go. There's a line integral in R3, by the way. R3 diagram if it's a line integral in R3. Line integrals connect to these two theorems. It is possible, if you're computing a line integral, that you might compute it with f of b minus f of a. It's possible that you might compute it as a flux of the curl, right? There's a couple of different possibilities. These are both worth entertaining, right? What the diagram also shows, well, shows is a wrong word, but what the diagram also strongly suggests is that divergence doesn't have anything to do with this question. Stay away from divergence. Try not to put divergence on your page. Bad look. Right? So likewise, there's not going to be any triple integrals. If you're computing a line integral like that, no triple integrals. Bad luck. Don't say the word Gauss or the word divergence. Right? All this stuff over here, all a bad look. Is everybody on board? Okay. All right. Okay. So this is what I mean by identifying your context on the diagram. All this stuff. Oh, let me see if my stylus will work again. I'll bet it will. Let's see, how's my charge? Hey, I'm all charged up. Good deal. Give me a second to put this back together. Okay. No. Come on. The little deals. Okay. All right, there we go. Okay, so, yeah. Okay, so, context from the diagram. Okay, compute the appropriate operator, it says. So, what does that mean? Back to the diagram. Let's suppose that I was asked to compute a flux. If I were asked to compute a flux, I must have been told what vector field I'm computing the flux of, and of course I must have also been told a surface through which I'm computing that flux. So by compute the appropriate operator, that says, all right, well, again, this is where flux is. That means that my vector field and my domain are also right here in column 2. What does the diagram tell me to do to this vector field? It tells me to compute the divergence. So go ahead. I think it's a good idea to just go ahead and once you've identified what the appropriate operator is, go ahead and do it. Because there's a couple of different possibilities. One possibility is you might get 0, in which case you know that there is an anti-curl, in which case Stokes' curl theorem might be a useful tool. Right? So that just the act of computing that divergence could be useful information for you. Now, the second possibility is that maybe you compute the appropriate operator here and you don't get 0. Oh, okay, well, I mean, there is another possibility, which is that, hey, maybe my surface, let's see here, maybe my surface has no boundary. Maybe my surface, think about what a surface would have to look like if it doesn't have a boundary curve. That surface would have to kind of close up to not have a boundary curve, and that means that your surface would be the boundary of a solid, in which case we can use Gauss's divergence theorem, and this divergence that we just got through computing, this divergence that we just got through computing is our integrand. Right? So there's a couple of different ways that computing that divergence can be useful. Said differently, computing whatever operator the diagram tells you to compute. Useful in a couple of different ways. Okay, so again, if you're looking at a flux, whatever vector field you've got, compute the divergence. If you've been asked to compute a line integral, don't compute divergence. Steer clear of divergence. Right? But if you've been asked to compute a line integral, whatever vector field is the integrand, compute the curl. If it's 0, it tells you that there's an antigradient, and you can use this theorem. If it's not 0, then that might be, whatever that curl is, would be the integrand for the resulting flux integral if you use Stokes' curl theorem. Again, useful in a couple of ways. Is everybody on board? All right. Okay. Yeah. So we've talked about the context. We've talked about, do what the diagram tells you to do, right? And then other than that, you've got candidate theorems to think about using. Look and see which ones seem like the most convenient to use. And don't forget, you might get geometrically lucky. Always worth a look. Always worth thinking about, hey, is there some awesome geometry argument that's going to make my problem easier? Might there be a symmetry that I can capitalize on? Always something to keep an eye out for, right? But other than that, the diagram tells you what your candidate theorems are. Do whatever seems most reasonable. Here we go. Let's see our first example. Okay, so here's a question as it might appear on an exam. Right? Notice it says compute a line integral. That tells me my context. In particular, notice this is a line integral of a vector field with 3 components. So I'm in 3 dimensions. Also, my curve that I've been given is parameterized with 3 coordinates. So we're in 3 dimensions. We're looking at a vector line integral in R3. And back to the diagram, let's see here, R3, vector line integral. Here's my context, right? Nothing over here is going to be relevant. You're not going to catch me writing divergence or triple integrals or saying the word Gauss. None of that, right? Because it just couldn't possibly be relevant. Yeah? Okay, let's see here. The diagram tells me, it seems, that whatever vector field I've been given here, apparently I should compute the curl of it. Apparently that might be useful. Okay, I'm going to follow the instructions. By the way, thank you to the diagram for making a helpful suggestion of something to do, right? So I'm going to take my vector field here. Let's see here. Take my vector field, and I'm going to compute the curl. There is a tedious aspect to computing curl, right? Make sure that you're good with that formula. You got to think about how you're going to memorize that. I suggest remembering it as being a symbolic determinant. I find that easiest. But anyway, make sure you're good with that. So we get, it seems, 1 minus 1 for the first coordinate. And then let's see here, 2x minus 2x for the second coordinate. And then let's see here, for the third coordinate, I get 2y minus 2y. I get the 0 vector. Everybody follow the algebra on that? If you didn't follow my algebra on that, make sure to look again at the formula for how to compute curl, right? And you want to think through, streamline your understanding of that formula so that you can compute that quickly, like I did here. Okay, curl was 0. That's good news. Let's go back to the diagram here. We got 0. Awesome. That tells me right off the bat there is an anti-gradient. Right? I can use the fundamental theorem of line integrals here. We have a good solution on the table. Right? But before we jump in and compute that way, let's ask, what about Stokes' curl theorem? Can I use Stokes' curl theorem here? Well, in order to be able to use Stokes' curl theorem, I would need for my curve to be a boundary. I would need for the given curve here to be a boundary of some surface. And I don't yet know, is my curve a boundary of some surface? Now again, you can jump on with the fundamental theorem and just do it that way, but I want to entertain all of our options first. Let's think through what are our options. Sometimes there's one good option and another even better option, right? So let's be open to that possibility. Is our curve a boundary of something? Hard question. Here's my curve. thing looks like, right? But whether this is a boundary or not, notice, I kind of need to distinguish this possibility from this possibility. Right? Here, it is a boundary of something. Here, it's not a boundary of something. So notice that the way I can tell those apart, I can distinguish those two possibilities by whether it starts and ends at the same point or whether it starts and ends at different points. This is just another little cool fact of geometry, that if your curve is a boundary of a surface, well, it's got to start and end at the same point. It has to be a closed curve. Yeah? Okay, so back to the diagram. Notice that means I can answer this question about whether or not my curve has an anti-boundary by computing that curve's boundary and seeing if I do or don't get 0. Does it start and end at the same point? Okay, and so again, that suggests a computation here. It suggests I need to, let's see here, cleaning up the picture first. I need to look at this curve, and I need to start plugging in values. This curve happened to come parameterized. Not that they always will, but since it has come parameterized, I'm going to need to plug in t equals 0. See what point I have? I'm going to need to plug in t equals 1. See what point I have, and see if they're the same point or not. And here we go. Let's see here. My starting point, plugging in t equals 0, I get 0, 1, 1. Alrighty, now let's look at plugging in t equals 1, and I get, let's see here, plug in t equals 1, okay, cosine of pi, so I get -1, comma, you know what, we're kind of done here. It's already clear that these are different points, but let's, for the sake of completeness, go ahead and keep plugging in. E to the power of 0 is 1, and then let's see here, e to the power of 2. Okay, so e squared. Everybody with me? This is not a closed curve. So I did not get boundary 0, so there is no anti-boundary surface. That means Stokes' theorem is off the table. There is no Stokes' theorem for this question. Stokes' theorem only applies to boundary curves. This is an open curve. It couldn't be a boundary of anything. No chance for Stokes' curl theorem here. Everybody with me? Okay. All right, so that was a crash and burn. Let's think through what we've got then. There's no possibility of using Stokes' curl theorem. Okay, you know what? My only good option is fundamental theorem of line integrals. And so I'm just going to proceed in the usual fundamental theorem of line integrals method. I'm going to find the anti-gradient by usual methods, and then I'm going to plug in to that formula. Everybody with me? And that's all details that I think y'all can handle. Yeah, let me just write down on here that this you're going to compute as f of b minus f of a. And of course, I've already computed the b and the a down there. Everybody happy? Now, look, I dragged this out in much gorier detail than I would expect y'all would, certainly document on an exam, right? The purpose of me dragging this out was to try to underscore and illustrate, there it is, how the diagram is useful, right? How you can use this diagram to strategize, Diagnose what kind of a question is this a Stokes' curl theorem question? No. Oh, okay. Is this a fundamental theorem of line integrals question? Oh, yeah, it is. Okay, cool. Right? The diagram just makes that easy. It tells you what to do, what questions to ask. Right? So take the help, if you will. I think it's extremely useful sort of organizing ideas in your mind for you. Strongly advise that y'all capitalize on that. Okay, now I've got several more examples. We're out of time for today, of course, but several more examples. We'll go through those next time. Hopefully then also to make some progress going back into Chapter 13. Remember, we've got that optimization stuff that we skipped in Chapter 13. But anyway, we'll pick up from here next time. See y'all later.